For this module, you will need the paper 10 Simple Rules for Better Figures. This paper is published in PLOS, Computational Biology. It is published by Nicolas Rougier and colleagues. It is an open access paper published in 2014. We are going to review it now. Scientific visualization is classically defined as the process of graphically displaying scientific data. However, this process is far from direct or automatic. There are so many different ways to represent the same data. This can be scatter plots, linear plots, bar plots, and pie charts, just to name a few. Furthermore, the same data using the same type of plots may be perceived very differently depending on who is looking at the figure. A more accurate definition for scientific visualization would be a graphical interface between people and data. In this short article, the authors do not pretend to explain everything about this interface. Rather, for that, you can see the introductory work which is cited. Instead, they aim to provide a basic set of rules to improve figure design and to explain some of the common pitfalls. Rule 1. Know your audience. Given the definition above, problems arise when how a visual is perceived differs significantly from the intent of the conveyor. Consequently, it is important to identify as early as possible in the design process the audience and the message the visual is to convey. The graphical design of the visual should be informed by this intent. If you are making a figure for yourself and your direct collaborators, you can possibly skip a number of steps in the design process because each of you knows what the figure is about. However, if you intend to publish a figure in a scientific journal, you should make sure your figure is correct and conveys all of the relevant information to a broader audience. Student audiences require special care since the goal for the situation is to explain a concept. In that case, you may have to add extra information to make sure the concept is fully understood. Finally, the general public may be the most difficult audience of all, since you need to design a simple, possibly approximated figure that reveals only the most salient part of your research. This has proven to be a difficult exercise, and here we are referred to Figure 1. Now let's look at Figure 1 together. Now you should have Figure 1 open. Figure 1, know your audience. This is a remake of a figure that was originally published in the New York Times in 2007. This new figure was made with matplotlib using approximated data. The data is made of 4 series: men, deaths and cases, women, deaths and cases, that could have been displayed using a classical double column bar plots. However, the layout used here is better for the intended audience. It exploits the fact that the number of new cases is always greater than the corresponding number of deaths to mix the two values. It also takes advantage of the reading direction, English left to right for the New York Times. This is in order to ease comparison between men and women, while the central labels give an immediate access to the main message of the figure. This is a self-contained figure that delivers a clear message on cancer deaths. However, it is not precise. The chosen layout makes it actually difficult to estimate the number of kidney cancer deaths because of its bottom position and the location of the labeled ticks at the top. While this is acceptable for a general audience publication, it would not be acceptable in a scientific publication if actual numerical values were not given anywhere else in the article. So take a clear look at Figure 1. Rule 2, identify your message. And I would like to remind you, now is a good time to have all of your figures open. You could print those up before listening to this module. Rule 2, identify your message. A figure is meant to express an idea or introduce some facts or a result that would be too long or nearly impossible to explain only with words, be it for an article or during a time-limited oral presentation. In this context, it is important to clearly identify the role of the figure. What is the underlying message, and how can a figure best express this message? Once clearly identified, this message will be a strong guide for the design of the figure. And this you can see in Figure 2. Only after identifying the message will it be worth the time to develop your figure, just as you would take the time to craft your words and sentences when writing an article only after deciding on the main points of the text. If your figure is able to convey a striking message at first glance, chances are increased that your article will draw more attention from the community. Rule 3, adapt the figure to the support medium. A figure can be displayed on a variety of media, such as a poster, a computer monitor, or a projection screen, as in the case of an oral presentation. It could be a sheet of paper or on a printed article. Each of these media represents different physical sizes for the figure, but more importantly, each of them implies different ways of viewing and interacting with the figure. For example, during an oral presentation, a figure will be displayed for a limited amount of time. Thus, the viewer must quickly understand what is displayed and what it represents while still listening to your explanation. In such a situation, the figure must be kept simple and the message must be visually salient in order to grab attention. And this can be shown in Figure 3. It is also important to keep in mind that during oral presentations, figures will be video projected and will be seen from a distance. And figure elements must consequently be made thicker, as in the case of lines, or bigger, as in the case of points, text. Colors should have strong contrast, and vertical text should be avoided. For a journal article, the situation is totally different because the reader is able to view the figure as long as necessary. This means a lot of details can be added along with complementary explanations in the caption. If we take into account the fact that more and more people now read articles on computer screens, they also have the possibility to zoom and drag the figure. Ideally, each type of support medium requires a different figure, and you should abandon the practice of extracting a figure from your article to be put as it is on your oral presentation. Rule 4. Captions are not optional. Whether describing an experimental setup, introducing a new model, or presenting new results, you cannot explain everything within the figure itself. A figure should be accompanied by a caption. The caption explains how to read the figure and provides additional precision for what cannot be graphically represented. This can be thought of as the explanation you would give during an oral presentation or in front of a poster, but with the difference that you can think in advance about the questions people would ask. For example, if you have a bar plot, do not expect the reader to guess the value of the different bars just by looking and measuring the relative heights on the figure. If numerical values are important, they must be provided elsewhere in your article or be written very clearly on the figure. Similarly, if there is a point of interest in the figure, make sure it is visually distinct, but do not hesitate to point it out in a caption. Rule 5. Do not trust the defaults. Any plotting library or software comes with a set of default settings. When the end user does not specify anything, these default settings are used to specify size, font, colors, styles, ticks, markers, and so forth. Here you can look at Figure 4. Virtually any setting can be specified, and you can usually recognize the specific style of each software package or library thanks to the choice of these default settings. Since these settings are to be used virtually for any type of plot, they are not fine-tuned for a specific type of plot. In other words, they are good enough for any plot, but they are best for none. All plots require at least some manual tuning of the different settings to better express the message, be it for making a precise plot more salient to a broader audience, or to choose the best color map for the nature of the data. For example, see Figure 4 for how to go from the default setting to a nicer visual in the case of this Matplotlib library. Rule 6. Use color effectively. Color is an important dimension in human vision and is consequently equally important in the design of a scientific figure. However, as explained by Edward Tufte, Color can be either your greatest ally or your worst enemy if not used properly. If you decide to use color, you should consider which colors to use and where to use them. For example, to highlight some element of a figure, you can color this element while keeping other elements gray or black. This provides an enhancing effect. However, if you have no such need, you need to ask yourself, is there any reason this plot is blue and not black? If you don't know the answer, just keep it black. The same holds true for color maps. Do not use the default color map unless there is an explicit reason to do so. Here, take a look at Figure 5. Color maps are traditionally classified into 3 main categories. These are sequential, one variation of a unique color used for quantitative data varying from low to high. Diverging, this is variation from one color to another, used to highlight deviation from a median value. Or qualitative, rapid variations of colors, used mainly for discrete or categorical data. Use the color map that is most relevant to your data. Lastly, avoid using too many similar colors since color blindness may make it difficult to discern some color differences. Rule 7. Do not mislead the reader. What distinguishes a scientific figure from other graphical work is the presence of data that needs to be shown as objectively as possible. A scientific figure is, by definition, tied to the data, and if you loosen this tie, you may unintentionally project a different message than intended. However, representing results objectively is not always straightforward. For example, a number of implicit choices made by the library or software that you're using that are meant to be accurate in most situations may also mislead the viewer under certain circumstances. If your software automatically rescales values, you might obtain an objective representation of the data that is nevertheless visually misleading. You have inadvertently misled your readers into visually believing something that does not exist in your data. You can also make explicit choices that are wrong by design, such as using pie charts or 3D charts to compare quantities. These two kinds of plots are known to induce an incorrect perception of quantities, and it requires some expertise to use them properly. As a rule of thumb, make sure to always use the simplest type of plot that can convey your message, and make sure to use labels, ticks, title, and the full range of values when relevant. Lastly, do not hesitate to ask colleagues and peers about their interpretation of your figures. And here you are referred to Figure 6. Rule 8. Avoid chart junk. Chart junk refers to all of the unnecessary or confusing visual elements found in a figure that do not improve the message or add confusion in worst case. For example, chart junk may include the use of too many colors, too many labels, colored background, useless grid lines, and so forth. Here you are referred to Figure 7. The term was first coined by Edward Tufte, in which he argues that any decorations that do not tell the viewer something new must be banned, regardless of the cause. It is all non-data ink or redundant data ink, and it is often chart junk, said Edward Tufte. Thus, in order to avoid chart junk, try to save ink or electrons in the computing error. Stephen Few reminds us in number 7, this is the reference number 7, that graphs should ideally represent all the data that is needed to see and understand what's meaningful. However, an element that could be considered chart junk in one figure can be justified in another. For example, the use of a background color in a regular plot is generally a bad idea because it does not bring useful information. However, in the right part of Figure 7, we use a gray background box to indicate the range. As you see, the range is plus or minus 1, as described in the caption. If you're in doubt, do not hesitate to consult the excellent blog of Kaiser Fung, and that is in reference 8, which explains quite clearly the concept of chart junk through many examples. Rule 9, message trumps beauty. Figures have been used in scientific literature since antiquity. Over the years, a lot of progress has been made, and each scientific domain has developed its own set of best practices. It is important to know these standards because they facilitate a more direct comparison between models, studies, or experiments. Most importantly, they can help you to spot obvious errors in your results. However, most of the time, you may need to design a brand new figure because there's no standard way of describing your research. In such a case, browsing the scientific literature is a good starting point. If some article displays a stunning figure to introduce results similar to yours, you might want to try to adapt the figure for your own needs. And here they say, note that we did not say copy, and you want to be careful with image copyright. If you turn to the web, you have to be very careful because the frontier between data visualization, infographics, design, and art are becoming thinner and thinner. There exists a myriad of online graphics in which aesthetic is the first criterion and the content comes in second place. Even if a lot of those graphics might be considered beautiful, most of them do not fit the scientific framework. Remember, in science, message and readability of the figure is the most important aspect, while beauty is only an option. And they demonstrate this or show this in Figure 8. So turn to Figure 8. Rule 10, get the right tool. There exist many tools that can make your life easier when creating figures, and knowing a few of them can help save you a lot of time. Depending on the type of visual you're trying to create, there is generally a dedicated tool that will do what you're trying to achieve. It is important to understand at this point that the software or library you're using to make a visualization can be different from the software or library you're using to conduct your research or analyze data. You can always export data in order to use another tool. Whether drawing a graph, designing a schema of your experiment, or plotting some data, there are open source tools for you. They're just waiting to be found and used. And below, the authors provide a small list of some of these open source tools for you to begin exploring.